I think we are just about ready to get started. So first of all, thank you all for coming today. We are here for a presentation from Alex Garcia as part of his thesis defense. And I'm not going to talk too much about Alex's research footprint. I'm going to let him talk about that. But what I think is really interesting as I sort of thought about my comments for prefacing his defense presentation today was really the broad nature of his activities while he's been in grad school. So research-wise, he's going to tell you about what has gone into his thesis, which is not actually an entire encompassing presentation on what he's done during grad school. He's worked on density profiles for the dark matter components of galaxies, trying to understand their sensitivity to formation history and input physics. He's worked on the metal content of galaxies, the development of simulations, and statistical inference methods as well. So there's, first of all, a broad impact there. But if you step back, his impact has also been pretty broad in terms of how he's engaged outside of the research portfolio itself. So as likely everyone here knows, Alex was previously a graduate student at the University of Florida, where he was in the master's program. And while he was there, he single-handedly rewrote the Intro Labs manual and associated software, which he also named Alex.
It stood for something, Astronomy Laboratory Exercises and Experiments.
Which won him an award for his teaching contributions at the University of Florida. He did that while doing research, while also acting as the assistant director for the Santa Fe Planetarium, literally taking on full night shows to, dozens of individuals, elementary school age up through retirees, on a weekly basis, guiding them through planetarium tours. And so he's had that kind of huge impact from teaching over to service and into research. That impact has continued here at the University of Virginia, where he's been deeply involved in the Dark Skies Bright Kids program. He's helped to arrange some of their after-school programs. He's also been ready to organize activities inside the department. And so his presence will be missed as a journal club organizer, which many of you are nodding to. We're missing that today to be here.
My bad.
But he's been actively involved internally in the development of or in the administration of the journal clubs. He's also been quick to volunteer also in our research organizations. He serves on the Student Postdoc Leadership Council within Cosmic AI, helping to make sure that the voices of students and postdocs is communicated back to the leadership to try to make sure we're doing the best job possible to represent those junior scientists. And so we're going to really miss the impact of Alex, not just in terms of the research component, but those many different axes which he's sort of built out over his time as a graduate student. And I think in many ways, most of all, it's setting that example for what it means to be a graduate student along those many different axes. So with that, I'm going to hand the floor over to Alex, who will tell us about his research, specifically about the coevolution of galaxies and their metal content, and a general study of theoretical astrophysics in the world of our computational modeling. So Alex, take it away.
Great, thanks. I'm going to turn down the lights here. So I'm really excited to be kicking off this sort of palooza of thesis defenses in the department over the next course of the month. And, for my money, no better way to kick things off than to have Paul in front of witnesses say nice things about me. So thank you, Paul. I want to reiterate Paul's comment. I want to thank everyone for being here, taking an hour out of your Friday morning to listen to me yap about galaxies, especially folks online who are zooming in from a number of different places. Just want to say thank you for everyone being here and supporting me today. Astronomy as a field is in this really sort of interesting era where we've got a lot of access to really high quality data and a lot of interesting comparisons to be made with this data. So for example, there you go. In the local universe, we've got these really high resolution, detailed observations of these systems that we know to be multi-scale and multi-phase that we call galaxies. Images like this are probably what you think of when you hear the term galaxy, but they portray these systems that undergo some interesting physical, some interesting chemical, and some interesting astrophysical evolution. And we can directly observe and study that evolution. But we also have observations of things way, way, way further away, i.e. way further back in time, that let us know that these things didn't just poof into existence, right? They have some detailed assembly history. They have some detailed evolutionary history that brings them to be in their current form. So the name of the game is how can we bridge our understanding from the early universe to what we see today? So that's been sort of the mission for the last 100 years, almost exactly 100 years at this point. And over the last 100 years, we've developed a series of sophisticated, dare I say good, set of ideas and theories for how galaxies form and evolve. So good, in fact, that we can take the pieces of the puzzle that we think we understand and throw them into a computer, and we get things like numerical simulations. Numerical simulations, of course, provide this really interesting temporal evolution of galaxies and make pretty movies that I can put in thesis talks. But they also offer these really sensitive and detailed laboratories for us to understand and test the pieces of the puzzle that we have put together. But I want to be clear, I want to be totally explicit right at the top of this talk. These things are experiments. A lot of the time, they don't always model all of the physics. In fact, basically none of the time they model all of the physics relevant for the universe. They have limitations, they have resolution issues, they're not converged, so on and so forth. Nevertheless, I hope to convince you over the next, I guess 45 minutes that these things are useful and can help us understand galaxy evolution. Maybe a bit of a cryptic statement, so let me put maybe more of a pin on this. If we think about the evolution of galaxy evolutionary simulations as a whole, and we flash back to sort of the stage 20 years ago, where these things came into their maturation, we have these really large n-body gravity-only efforts, which simulate huge swaths, hundreds of millions of light years, hundreds of megaparsecs across, and again, just gravity-only going on here. And we can already see we do an interesting job reproducing things like the large-scale structure of the universe. But in more detail, other than making pretty images, you can go into this and perform a pretty simple exercise. That being, I can go to all of the nodes, all of the filaments, and all of the voids in my system and count the number of galaxies I have. So if I count the number of galaxies I have and plot it as a function of mass, you have what's known as the mass function. The y-axis, again, number of galaxies. On the x-axis, we've got their mass. And if you go into these simulations and you do this exercise, you get this sort of red line, which is a power law relation in this space. But we also have observations. We can do this same sort of exercise in the observations, and doing so yields this blue line. It looks totally different than the red line. Okay, so immediately we can recognize something is going on. Gravity by itself, the only thing we're modeling in these simulations, is just too efficient at making galaxies. We need something to regulate the mass and the growth of galaxies. So what's doing it? As it turns out, it's the things we forgot to model, right? The things that aren't gravity. The things like gas, which can cool, it can heat, it can expand, it can contract, it can form stars. Stars which have some evolution associated with them. Stars which can die and return their mass and energy back into the system. Stars which can form black holes which can grow, accrete, and make supermassive black holes, which can drive winds and jets from the center of the galaxy. Things that I'm going to be sort of collectively referring to here as the broad term baryons. Baryons here, maybe for the experts in the room, right, is just things that interact with the standard model, i.e. not dark matter. And the physics of all of these interesting things gives rise to this sort of cycle that you probably saw in the video as you were walking in, we were setting up earlier today. And this baryon cycle, or this sort of gas cycle, is sort of analogous to what you can think of as like the water cycle in ecology. Right? You've got gas clouds in the circumgalactic and intergalactic medium, which can rain down material onto the system. This new material seeds new star formation. These stars evolve, grow, and then die. At the end of their lives, they return mass and energy back into the system. They can mix around the gas within the disk of the galaxy, or they can launch these powerful outflows, which can either escape the system entirely or rain back down, beginning the cycle anew. And so it's really this baryon cycle, this gas cycle, that's causing the difference that we're seeing in this mass function. Right? Collectively, I'm also going to refer to this as sort of feedback. Feedback from stars, feedback from black holes is what's causing this. And so the question of the hour, the question of the last 20 years, is how can we most accurately model this baryon cycle? And to answer this question, we need to also ask similar questions, like what observations do we need to actually constrain our observation, or excuse me, our models, and let us know with some certainty what's going on? And what important lessons do numerical simulations hold? Even if they're crude, even if they have these issues, even if some of them might be just straight up wrong, what lessons can they teach us? So this brings me pretty neatly to the title of my talk, right? Metallicity as a tracer of this baryon cycle in these modern cosmological simulations. Okay, I spent a little bit of time describing baryon cycle, but let me go through the rest of this. We'll start with metals, right? If you're not an astronomer, metals, right, is probably a sort of strange term. An astronomer, we mean metals is anything that's not hydrogen or helium. Okay, why do we do this silly convention? Well, at the beginning of the universe, there was this Big Bang, right? And shortly thereafter, we have Big Bang nucleosynthesis, the byproducts of which is a lot of hydrogen, a little bit of helium, and basically nothing else. And so at the beginning of time, we've got basically just hydrogen and helium. Anything else, carbon, nitrogen, oxygen, lead, gold, iron, nickel, et cetera, was formed after the Big Bang. It's the results of things like stars that have some evolutionary history associated with them. I promise there's not so many memes in every slide, just this one. And so the really great thing about these metals, especially in the gas phase, which I'll be primarily talking about with one exception today, is that they move around with this gas flow, right? They're made in the stars. When the stars die, they eject them back into the system, and then they follow along in this gas cycle. And we can sort of directly observe these metals, and so we can get some proxy observationally of the metal content of galaxies or metallicity. Last thing I'll note here is we're going to be using these sort of weird units, log O over H plus 12. Really, this is sort of your like pollution term, right? Oxygen, metals pollute your pristine environment relative to your pristine hydrogen environment. So note on the units there. Okay, last thing to go over is modern cosmological simulations, right? I talked about these things 20 years ago, which were just gravity only. But now they're a little bit more sophisticated. They include things like star formation, stellar evolution, supermassive black holes. There's feedback from stars and black holes, gas cooling, heating, et cetera. And critically for this talk, right, chemical enrichment, the production of these metals. These simulations are typically, well, not always, in these large actual like boxes with some random looking initial conditions. And as we press go on the simulation, we can see structure start to form, things to collapse, and we see the large-scale structure emerge. Now, some of you might be thinking, right, oh, hey, that's the thing I study that you see on the right-hand side, right? And so a lot of these things, of course, are things that people actually study professionally, right? And so there are some uncertainties associated with each of these individual steps, and there's going to be doubly uncertainties when we try and put them all self-consistently into one different model. And so the problem that sort of arises here is that there's different ways to do this. And to sort of illustrate this, this is a very similar video to what I just showed you, now showing in 8 different simulation models instead of just one. And as we get closer and closer to the present day, redshift 0, z is equal to 0, we can see that these models pretty strongly diverge in their predictions. So how do we constrain this? How do we get a sense of which one of these things is right, which one of these things is wrong, which one of them is closer, which one of them is further? So I took 10 minutes to describe the title of my talk, right? Now we're going to turn the page figuratively and literally in the thesis and think about what my work has been in this space. And specifically, as Paul sort of mentioned, I'm going to be interested in what the metal content of these galaxies looks like. Why the metal content? Well, because they're directly observable. And I also want to answer the questions about what lessons these numerical simulations can teach us about how galaxies actually evolve. All, of course, in service of answering this question, how do we accurately model the baryon cycle? So I'm going to be doing this on basically two different ways. Way number one that we're going to start with is looking at sort of global population integrated scales. And then a little bit later, we're going to zoom in on individual galaxies and look at how this changes within systems. So without further ado, we'll go ahead and get started on the integrated scales. So on integrated scales, you can sort of think of taking an aperture and placing it over a single galaxy and calculating a metallicity from this, from things like emission diagnostics. And you can calculate a mass of the galaxy. So you can put these two things together in a mass metallicity relation, or MZR. And again, this is sort of what it looks, sort of blank version of it, right? On the y-axis, we've got these weird log over h plus 12 units. On the x-axis, we've got stellar mass. And if we go in and we do this not just for one galaxy, but populations of galaxies in observations, we get the relationship that looks something like this. It's got like a power law at low masses, and then at high masses, it sort of flattens out a bit. And it's got some scatter associated with it, right? Some non-negligible scatter. If you look in detail in the scatter here, you can notice that there is some correlation with a third parameter, the number of stars you're forming, your star formation rate, such that galaxies with lower metallicities tend to have higher star formation rates. There's anti-correlation there. Okay, so why is that happening? That seems like maybe a sort of strange thing on its face. Well, to understand this, I'm a galaxy simulations person. We're going to run a galaxy simulation. Here we've got our galaxy. We're going to assume that it's already formed, and then we're going to run a simulation on it. Right? We're going to assume it's formed. It's got some stellar mass associated with it. It's got some metallicity, such that it sits exactly on the median MCR at the time of the start of our simulation. And we're going to start our simulation, and we're going to let the baryon cycle sort of happen. We're going to start raining down and accreting gas. Okay, and so we're going to start accreting gas. This gas from the circumgalactic and intergalactic medium is pristine. It's mostly hydrogen. And so again, if we're thinking log O over H units, if we increase H, the ratio is going to go down. So we're going to tick down our metallicities. But this new gas, as I also mentioned, seeds new star formation. And so we're also going to be persistently increasing our star formation rate as we tick down our metallicity. Now, these stars, of course, are also forming metals, which eventually make their way back to the ISM, but they're also depleting this gas reservoir. And so if we're forming more metals, we're going to move up in this space. And if we're depleting our gas reservoir, we're going to go down in star formation rate space. So you get this really nice anti-correlation. And of course, the baryon cycle doesn't just happen in steps. And so if we let this sort of play out on and on and on, and we run our simulation not just for one galaxy, but for several galaxies, we end up with this sort of stratified scatter about the mass metallicity relationship. Again, things with lower metallicity, higher star formation rate, anti-correlation there. And so the experiment that we're going to run, this is what we see in observations. The experiment that we're going to run is we're going to take 4 of these simulation models, Illustris, TNG, Eagle, and Simba. Yes, that's Simba. And we're going to ask how sensitive are we to the different assumptions that these models make. Okay, I didn't just pick these 4 models out of a hat, and it's not just because I like The Lion King. But these models are actually relatively similar to each other, meaning that they are approximately the same resolution. They simulate approximately the same volume of a universe. And a lot of their things like star formation rate and chemical enrichment and feedback from stars are done in an approximately similar way. And so if we're going to be sensitive to these detailed assumptions, it's going to be very subtle. Right? And so let's take a look. Let's see how sensitive are we to these different assumptions. I'm going to show here the mass metallicity relationship in the 4 simulation models on the top. To maybe guide your eye, I've also got observations down here in the bottom left. And the first thing you can notice is that we have some detailed anti-correlation between metallicity and star formation rate. Right? It's color-coded here by star formation rate, where yellow things are more star forming and purple are less. And again, you can see yellow things sort of cluster towards the bottom pretty generically in these simulations, right? Okay, check. We get at least that part right. But if you take, more than a cursory glance and you look at this, it's pretty clear immediately that Illustris is doing something slightly different than TNG. TNG is doing something slightly different than Simba. Simba is doing something slightly different than Eagle. And I contend that this is due to these different physical implementations. And to sort of pull back the curtain and to demystify this, we're going to pick a little bit on Simba. We're going to do this twice. Why am I picking on Simba? One, it's easy. Two, I like it. And so we're going to pick on Simba. In the Simba model, the feedback from stars can be modeled with some equation that sets the mass loading factors, this eta, which are themselves a function of stellar mass, right? So what do these mass loading factors do? They're just the amount of mass entrained when a star explodes, right? So it's set by some equation in these models. And it sort of has this two equations, right? On one mass, it's doing one thing, and another, it's doing another. And it's got this turnover mass m naught, right? And so m naught, if you're above this, you're doing something. M naught, you're doing something else. So if we plot m naught on this diagram, you can see that this is exactly where we see the difference in the different model, or excuse me, the difference between the different correlations about the MZR. And so this is something physical insofar as this is something we prescribed into our models, and it has a distinct impact on what's going on here. Okay, so what I've shown you this far is just the local universe stuff, so to speak, in these simulations. What if we go further back in time and measure how these things change? Do they help? Do they converge onto one result? The answer is no. They're also pretty different, right? Again, mass-metallicity relationship in a number of these different models. They're, again, at face value doing something sensible, or at least 3 of the 4 of them are doing something sensible. As you go further and further back in time, closer and closer to the Big Bang, you have less and less metals, which makes sense, right? You haven't had enough time for stars to pollute your environment and give rise to the increased metal content that we see in the local universe. But again, looking at this again in more detail, Illustris is doing something different than TNG. TNG is doing something different than Eagle. Eagle is doing something different than Simba. And again, this is just because of the different physical implementations. And to really, again, put a point on this, we're going to make fun of Simba again. Specifically, we're going to look at these mass loading factors, right? This is my biggest gripe with the Simba model, if you can't tell, is that they have some redshift dependence, meaning that above redshift 3, they do one thing, and below redshift 3, they do something else. And so if we look at the evolution of the Simba model about redshift 3, you can see that it does something different, and it has a distinct impact. And it does something sort of, in my opinion, non-physical, right? As you go further back in time from the present day redshift 0 to redshift 3, your systems are getting less and less metal rich. Makes sense. You're getting closer and closer to the Big Bang. But then systems at redshift 8, like a few 100 million years after the Big Bang, are like the same metallicity as the things in the local universe. That's nuts. That's not right. But this is purely a feature of the model going on. Right, and so what I really want to impress upon you with this is how sensitive are we to these different assumptions? The answer is very, right? Even in individual models, like little tweaks that we make for sort of justified reasons in the paper can have huge impacts on our ending results. Okay, and so there's been some claims in the evolution or in the observational literature that the 3-parameter relationship, mass, metallicity, and star formation rate, doesn't evolve with time. It's redshift invariant. Moreover, you can explain this relationship with this equation, right, which looks something like y is equal to mx plus b, right? Meaning that at any point in the universe's history, if I give you a galaxy's stellar mass and star formation rate, I can predict its metallicity using just a single linear relationship with 3 free parameters. Wow, that'd be pretty cool, right? Maybe a neat trick of the universe to do. But basically, this has 2 implications for the things I just showed. This means that this single equation should be able to explain everything that we see about the mass-metallicity relationship, right? The scatter about it and the evolution of the scatter, as well as things like as the total evolution of the normalization, right? How metal content is the average galaxy further back in time. This equation purports to be able to do this exactly. Okay, so let's take a further look at this claim in the simulations and see if we can learn something. First thing we're going to do is we're going to make a simplifying assumption. We're just going to look in a thin mass spin so that the mass term sort of drops out. And we're going to just say that the gas phase metallicity should be proportional to the negative log of star formation rate. Okay. And if we look at this in the simulations, this relationship purports that this constant proportionality in here should be invariant with time, meaning we should see a negative relationship between star formation rate and gas phase metallicity that is the same at every redshift we look. Okay, we take a look at this. This is sort of not the case. We see the negative relationship in each of these different models. Here, this is sort of like an offset from the median relation, but as a function of star formation rate. At redshift 0, it's doing one thing in each of the different models, notably something different in each of the different models. And then as you go further and further back in time towards higher redshift, more red lines here, the detailed shape of the slope actually changes. Okay, so this claim doesn't necessarily hold in the simulations for the scatter about the mass metallicity relationship. Interesting. Maybe it says something about the normalization. Let's check the second claim. Again, we're going to assume something about the average evolution, right? We're going to say that the average gas phase metallicity at any point in time can be prescribed by assuming some average stellar mass and some average star formation rate. And again, this relationship purports that these constants, M, alpha, and beta, and B, shouldn't actually change with time, meaning that this should have really good predictions for the mass metallicity relationship throughout the history of the universe. Okay, so let's look at this again in the simulations. On the left-hand side, I've got something I showed before, the true mass metallicity relationships. If you go in and load in the data from these simulations. In the middle panel, I've got the predictions, right? If you take this equation and plug in an average mass and average star formation rate for a number of galaxies in these models, that's the prediction. And on the right, you've got the residuals. Again, we see that the model is not doing super well. In particular, if you look at the shape of these things, for like illustrious and TNG specifically, you get a much more linear relationship. Sort of makes sense, right? This is a linear regression. But it has some other detailed evolution associated with it, meaning that as you go further and back in time, the predictions actually get further away from the true observations. Okay, so both of these claims that this single relationship can describe the mass metallicity relationship through time appear to be false in our simulations. So this tells us one of two different things. If this equation is true in the observations, this is a really, really, really strong test of our models. If this is what is going on in the universe, none of the models that I've looked at to this point actually do it. And so this has a lot of really potential constraining power for our simulations. But if you were to do similar tests in the observational literature and come up with similar answers, meaning that there is some evolution of this relationship, you can't just explain the entire mass metallicity relationship with one linear regression. How much information do we just lose by making that assumption, right? The mass metallicity relationship, as I sort of showed, is this like complex interplay of things like gas accretion, stellar feedback, outflows, chemical enrichment, so on and so forth. Can that really be explained by a single linear regression? It'd be kind of awesome if it did, right? But maybe naively, it seems kind of far-fetched, right? So this is, again, should highlight metallicity as a sensitive tracer of these things and can provide really important constraints either on our physical universe or in our or in our simulations. Now, everything I presented to this point on the MZR has been in the gas phase, right? There's more than one phase that we can look at in galaxies. We can also look at the stellar metallicities, right? Stars have some metallicity associated with them. They adopt this metallicity from their natal gas clouds. And so they're sort of like a fossil record of a galaxy. The metallicity of a star just tells us about the metallicity of the system when it formed, right? And these things take some time to evolve. Some of them die really quickly, but some of them live hundreds of millions of years, if not billions of years, and give us some detailed archaeological history of the galaxy. And it's, I won't belabor this point, right? If you look at the mass metallicity relationship, now looking at stellar metallicities in slightly different units, first thing you can notice, the different simulations do different things, right? Okay, I'm not going to belabor that point. But they do different things, not just at redshift 0 in the present day, but also further back in time. Stellar metallicities are a little more difficult to actually get observationally, especially further back in time, because they require these sensitive absorption diagnostics, but can also provide important constraints. So we don't just have one way to do this, we can do this in multiple different ways. And so I hope this sort of highlights integrated scales as a really useful tool, right? Even nominally pretty similar models, things that we know and implemented in very similar ways can give a huge diversity of results. So there's a lot of sensitivity here to be leveraged into the future. And again, highlights metallicity as this key observable to actually do this. Great. So now we're going to move from the integrated scales. We're going to zoom in on individual systems, and we're going to look on resolved scales. To this point, we sort of made this simplifying assumption that a galaxy has a metallicity. In detail, this is not true. Metallicity can be distributed throughout the entire system. The baryon cycle doesn't happen everywhere all at once. It can happen at different places at different times and different time scales. And so if you look in individual galaxies, these individual galaxies have some detailed metallicity shape associated with them. Things that I'm going to be referring to here as a metallicity gradient. And why gradients? Well, they tend to have more metals in the interiors than they do on the outskirts. And typically, especially in observations, this is fit with a single, again, linear regression. And we quote the slope as the metallicity gradient of a galaxy. Why do they have this sort of shape? Well, you can sort of think of a galaxy forming inside out. You're going to have more stars form in the center faster than on the outskirts. These stars are, again, the things making the metals and returning them back into the ISM. And so if you look at the metal content, you build up your metal content faster, or you have more stars, and you get this sort of negative metallicity gradient because of this inside-out formation. But like the mass metallicity relationship, this isn't something static. Things aren't just always fixed like this. There can be some evolution associated with this. And again, in the gas phase, there's a number of different ways that we can actually modify or change this. So there's specifically 3 ways that I want to sort of highlight here. One is radial advection. That's a really fancy term for gas mixing. Stuff can mix within the entire disk and redistribute metals. You can form new metals, right? Star formation and chemical enrichment is not things that just happen once. It's a continually ongoing process. And you can have accretion from metal poor gas onto the galaxy, right? You can think about, again, we increase H, our ratio is going to go down. You can do this in specific places more systematically than others. So what is each of these going to do? We've got radial advection, metal mixing. We're going to work to homogenize our system. We're going to flatten our metallicity gradient, so to speak. And all of the metals are going to be evenly distributed out throughout the entire galaxy. If we just let metal production go on, right, again, we've got more stars in the interior than the outskirts, and so we're going to form the more metals faster in the middle, and so our gradient's going to get steeper and steeper and steeper and steeper. And then accretion from metal poor gas in the cosmic web, well, this can have really subtle effects depending on where it lands, right? There's some claims that if you land and dump a whole bunch of pristine gas in the middle, and you lower your ratio just in the middle but not on the outskirts, you can sort of like create a kink in this profile, which would do something weird if you fit this with a single linear regression. But you can also put it on the end, and it'll do something slightly different, right? So there's some detailed sensitivity to where and when and how these processes happen. Great. So now the experiment that I'm going to do here is using totally different simulation models. So before I was using sort of even-handed similar models. Now I'm going to be using more highly different ones, things that we expect to be totally different. And it's going to come in the form of feedback, right? And we're going to use smooth feedback versus what's called bursty feedback. So why do we call it bursty feedback? Well, in the smooth feedback models, this is it's not playing yet, but the video that you saw a number of times already, you've got this system where you can accrete gas, form stars, it'll blow winds out, yes, but it's not doing so in like an ejective or destructive way. But in bursty feedback, you're doing this in an ejective and destructive way really, really rapidly, and your galaxy can literally blow up, right? If you imagine, right, if you put a bomb in the center of your galaxy and blow it up, your gas content, your metal content is probably going to be redistributed in some meaningful way, right? There's no way your system is going to just survive blowing up every 10 million years or so. And sort of to put this another way, right, if you look at the star formation rate histories in these bursty feedback models, this happens episodically and it happens frequently and is triggered by a whole bunch of star formation all at once. These stars then blow out the gas and quench the galaxy, or basically quench the galaxy, and it goes through these sort of episodes of this. Whereas in the smooth feedback models, you have some variability, yes, but it's mostly pretty smooth for the most part. Okay, and so let's look at the metallicity gradients in these different models. We're going to start with the smooth feedback model. Here you can see an image of one particular galaxy from one of these smooth feedback models. On the top left, you've got its gas mass, and on the top right, you've got its metal content. And if you just sort of reduce the metal content in the top right to a one-dimensional profile like we were doing before as a function of radius, and fit it with a line, you can see, it does okay, but you get this really strong negative metallicity gradient in this dashed red line. If we look in the bursty feedback models, again, we expect to see a huge difference. Galaxies blowing up, your gas content is way, way, way more chaotic. There's not even really a disk or anything going on here. And your metal content follows sort of suit, right? There's a whole bunch of stuff everywhere. And so your metals are everywhere. If you sort of make a radial profile and fit it with a line, you get a flat line. And so this is true generically. It's not just in these two galaxies that I cherry picked, right? If you look at all of these galaxies across a whole range of times, all the way back to something like redshift 10, a few 100 million years after the Big Bang, we can generally see that bursty feedback models on the top in sort of these red colors are much flatter than they are in the smooth feedback models. There's a lot of subtleties going on here, right? Again, thinking about some of these smooth feedback models that I'm using, some of the names you probably recognize from the last part of the talk. There are some subtle differences between these, but writ large, bursty feedback models have mostly flat gradients throughout all of cosmic time, whereas the smooth feedback models have much more negative gradients. Great. This is a really excellent test that we can do. We should be able to measure metallicity gradients pretty cleanly in the high redshift universe and say something profound about the nature of feedback. Is it smooth or is it more bursty? And so we started to begun to do this, we being the field, not necessarily me. And so I also have observations on here in gray from a wide variety of epochs. Pretty much everything above redshift 4 is from JWST. And sort of the consensus to date, although, again, there's a lot to be done on this front, is that things seem to be more preferring bursty feedback models, this ejective, explosive version. I want to also highlight here, right, how, again, I digged on a linear regression before. It's only fair that I do it again here. If, as you probably saw, these metallicity profiles as a function of radius aren't necessarily well posed as single linear regressions. There can be some subtleties going on here. And so we also have a paper exploring beyond a single linear gradient, doing something a little more complex to understand, again, why we're seeing the different shape. We can think again about our different production and formation and destruction mechanisms for gradients. And in particular, the two I'll highlight here are metal production and radial advection. You can pretty clearly sort of think of a scenario where you've got some enrichment-dominated region where you're steepening your metallicity gradient, which then transitions into a mixing-dominated region where you have a much flatter gradients, right? These things don't, again, happen all everywhere at the same time. And somewhere in between, you sort of meet in the middle, which in this paper, we call the break radius. And we use some sort of loose timescale arguments to make some comparisons saying that when the gas mixing timescale becomes approximately an order of magnitude worse than the enrichment timescale, this is where sort of we see this transition region between the two. But of course, this sort of assumes that feedback is smooth, right? If your system is blowing up every once in a while, gas mixing is going to be way, way more efficient than your chemical enrichment. And so what this would look like in a bursty feedback model, if you would even see a break radius in these models, it's not so clear. And so hopefully, yeah, resolved scales. This highlights that we're really good at telling things that are obviously different to be obviously different. And they produce really different metallicity gradients and metallicity profiles if you don't like linear regressions. And highlights again, what do these different models predict? What are the sensitive tests that we can perform to do this? So in return, again, to my central questions of this talk, right? How can we most accurately model the Baryon cycle? Well, I hope I've convinced you that metallicity is a great way to do this, and that important lessons, there's a ton of them that we can learn from these numerical simulations. But I maybe want to leave you off on sort of a provocative note, is can we do better? Can we? Right. So it's pretty clear in cases where something totally different is going on, these bursty feedback models, right? Yeah, like, yeah, okay, that galaxy's blowing up, that one's not, right? It's pretty easy to tell the two apart. In cases of the MZR, when I talked about the nominally similar models, sometimes there's some ways we can think really carefully about these things and understand the detailed sensitivities to things like mass loading factors. I can identify these different equations and say, okay, I know this is probably what's going on. But it's actually like, I picked on Simba because it was easy, right? But if I tried to pick on any of these other models, it becomes substantially more difficult. Right? There's a number of things that are going on that could drive differences in the metal content of galaxies. Identifying which property or which feature of the simulation model is directly causing the difference in the metal content. It's a really difficult task. Like, trust me, I tried. And it's not so straightforward to do. Worse yet, perhaps impossible, I might even say, at this point in the field, is we don't actually know how sensitive we are to our detailed assumptions within a single model. Right? If I change supernova feedback from 10 to the 51 ergs to 1.1 times 10 to the 51 ergs, how does that impact my system? I have literally no idea, right? And so understanding this is a really key area for the future. And so with this, one of the things that I'm interested in doing in the future and plan on doing as part of my postdoc is thinking about, can we run these simulation models with different physics variations, right? So here I'm showing a couple Milky Way mass galaxies. I didn't run these simulations, but I've helped analyze them. And we're just varying the supernova physics, AGN physics, and things like cosmology and dark matter to understand what's going on. We're making very subtle, detailed variations and understanding the extent to which these things change our models. And as you can see, maybe by this sort of collage that I've put together, it has pretty substantial impacts on the resulting galaxy. This thing is supposed to look like a Milky Way. Right? Whether or not it looks like a Milky Way, I think is maybe subjective, but we can sort of think about this in more concrete and understanding ways by using these detailed sensitivities. Of course, this allows things like data-driven exploration, which is great for machine learning, which is also great for funding right now. So that's really helpful. But of course, they allow these really nice, quick, relatively cheap parameter explanations. And you can actually answer questions like what's actually going on here. So before I leave up my conclusion slide, I, of course, want to thank some people, some acknowledgements. I want to say at first, I had a bunch of fun putting together these slides, probably too much fun, as you might see here in a minute. But of course, I want to thank a number of people along the way. This talk, of course, started with Paul saying nice things about me. Now I have to return the favor. I first, of course, want to acknowledge and thank Paul for being an excellent mentor throughout the course of 2 years. I told you I had too much fun. It gets worse than this. Yeah, he's usually happier than this. But I, of course, want to say thank you for sending me to conferences, sometimes reading papers, sometimes answering Slacks. Of course, being an excellent mentor for the last 5 years. I really, truly appreciate that. I want to thank everyone in Paul's group, with Dhruv included, Dhruv, who wins the award for being here from the furthest today. He was in Seattle yesterday. He's here today. So thanks, Dhruv. And everyone else in Paul's group. I want to thank you for being not only great, research mentors and collaborators, but really great friends. and being someone I can complain about Paul with. Yes. I, of course, want to thank my family as well. They emerged from the flames. My two sisters, my mom, my dad, Jody, Dan, my aunt, uncle, grandpa, Abby, Molly, Brian, Jennifer, all of my family for being loving, caring, supportive for the last 5 years and being someone I can complain about Paul with. Promise not everyone's going to have that. I, of course, want to thank, my scientific and research mentors who aren't necessarily at the university, Lars, Lisa, Katie, Sarah, James Alberry, who works at the planetarium in Gainesville, and Mariangela Asante for being really helpful along the way and helping me grow as a scientist and as a person. I also want to thank these miscreants, the undergrads that I've worked with for the last couple of years. Olivia, Martin, Ilum, Zach, Malhar, Laura, Danny, Caitlin, and Davis, as well as Larry and Jack. Larry and Jack, if you're online, you need to get a LinkedIn or something so I can add a photo of you next time. But of course, I really appreciate working with you guys. I've learned more in my time working with you, collaborating with you, teaching with you than I have basically the rest of grad school. So I appreciate that. And the 1.2 billion people who I didn't explicitly thank, I want to thank everyone for being helpful, for being friendly, being really great, not just scientific people to talk to, but friends and collaborators. I realized putting this together that I wear the same shirt a lot. And so I think with my postdoc money, I'm going to buy a new wardrobe. But speaking of money, right, I have to thank the University of Florida, University of Virginia, and Cosmic AI for paying me, right? I enjoy being paid. I enjoy science. I especially enjoy making a living doing it. And so I, of course, have to thank these folks. And just to be 100% totally cover all my bases, I want to thank everyone who I didn't explicitly just thank, viewers like you. And so with that, I'll sort of leave up my conclusions. I'm happy to take any questions.
Any questions for Alex? Right there.
So there's this you have like bursty and smooth feedback. Smooth feedback to me is like, well, let me ask you this way. Do you have a physical motivation from observations that tells you maybe bursty feedback makes sense? Are there observations of galaxies in the process of exploding or undergoing one of these chaotic destructive events that are motivating you to put that in your simulation?
Yeah, I didn't mention this in the talk, but the difference between bursty and smooth feedback is how you treat the ISM, right? In these simulations, if you want to prevent stars from forming, you need to prevent gas from collapsing, right? And so in the smooth feedback models, you do this with some subgrid pressure term. In the explicit models, in the bursty models, you have some explicit resolution that you can actually use to prevent gas from collapsing. So that's physically where that comes from in terms of the simulations. Whether or not it's motivated, there are things like the core cusp problem in low mass galaxies, whether or not you have your interior density can be cored or cusped. One of the ways that you can sort of think about solving this is with bursty feedback or alternative dark matter models. Another thing like high redshift UV luminosity functions, really great that Aaron was here yesterday, gave a talk about this. And one of the ways you can sort of explain these really luminous things in the early universe is that they're going through these burst phases. And so they're really, really, really bright in the UV. And so that's why you see these overabundance, right? Just because the thing is really bright. So there are a number of different tests or probes that you can use. There is some evidence that feedback, especially in the early universe, might be bursty.
Yes, so thank you, first of all, for this wonderful talk. Lots of pictures and videos. So my question was similar related to that. So as an observer and observing galaxies and reading literature, you seem to remember that the bursty gradient might depend, or in some cases does depend on the mass of the galaxy, right? So we have these beautiful, like our own Milky Way type galaxies with beautiful gradients, majestic gradients, but then we have these dwarf galaxies that are more homogeneous.
Yeah, that's exactly right.
So was that included, or is that, perhaps I missed the slide where there was?
Yeah.
I could imagine that. And there was some, I think Manucci had another paper mentioning that there might be like a fundamental, a metallicity gradient relationship where they just normalized by the luminosity of the galaxy. At least that was a claim 2010, 2020.
Yeah, agreed. So to the first question, and let me hide the floating mini controls. So to the first question, does mass matter in metallicity gradient? Yes, it does, right? So I didn't have a slide on this, something we totally looked at in the paper. In this plot, you can maybe sort of see this. In a lot of these smooth feedback models where large boxes, as you go further and further back in time, you have less galaxies, particularly less massive galaxies. And so you can sort of see, like, as I go from redshift 0 to redshift 10, in these smooth feedback models, it keeps going down and down and down, and then maybe at redshift 6 or something, it ticks back up, right? This is a mass dependence. This isn't necessarily something physical. Indeed, we tend to see, as you can sort of see here, galaxies with lower mass, right? The things we have more of at high redshift tend to have flatter metallicity gradients than the really big things. Yeah, and yeah, there's the linear relationship that I was sort of criticizing here in this slide. This, yeah, I didn't say its name because I hate its name, right? It's the fundamental metallicity relation, right? I don't think it's so fundamental, in case that wasn't clear. And so I tried to be fair. Yeah, there is this three-parameter correlation with the overall metallicity. You could imagine that there might be something, especially in like a bursty feedback model with metallicity gradients, right? As you're forming stars, you get a nice metallicity gradient, and then your stars go off and boom, wipe out your entire system, and so you get a flatter gradient. We didn't see too much evidence of this in the simulations, but it's unclear if there's some like phase offset between star formation and when your metallicity gradient flattens, and so it wasn't immediately obvious.
Got a couple. We'll go here first and down the road. Yep.
Thanks for a great talk, Alex. It's easy to follow. So like this actually is a question from yesterday's colloquium, like follow, because I could see that even on your results, there was something going off with the high redshift, which was the same thing case yesterday. But I think like their way was, I mean, they were focusing on like changing the number of galaxies, like the way they find galaxies in the first place. So it was essentially changing that algorithm, that structure of finding the number of galaxies, than simply just changing like the parameters that they would do eventually, than simply changing the physics. So do you think that that would be something that you will be looking to as well, like a combination of actually changing the algorithm, if that does impact your results?
It's a fantastic question. Yeah. So these things are calibrated at redshift 0, right? There's an important question: is the physics of redshift 0 the same as the physics of redshift 10? Right? It's an open question. And then, like, do my structure finders work on beautiful, grand design spiral galaxies and also these like clumpy, weird looking things at redshift 10? Do they work equivalently well on that? I don't have a straightforward answer to that, and certainly something I'm interested in trying to answer.
Thanks for the great talk. So I was wondering, one observer got a metallicity gradient and trying to compare with this suite of cosmological simulation. Like sometimes it may be consistent to one model and it may be consistent to another model. So I was wondering, in that case, is this like a good practice to compare it with multiple models, and how we should interpret the difference?
It's a really great question. Yeah. There's not a straightforward answer to this, right? I think that on population levels, it's probably a fair comparison to say, like the mass metallicity relationship, for example, might look totally different on a population level between one simulation versus another versus observations, and maybe you can rule something out there. I think on the individual galaxy level, it becomes much, 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 much trickier, right? And there's a question of like, if I see the exact metallicity gradient in an observed galaxy versus a simulated galaxy, did I form from identical processes? How do I know? Is there a way I can validate that? So something definitely you have to think carefully about as you translate between one space to the other. One of the things I didn't even mention here, it's particularly relevant. We get metallicities from the gas phase from emission line diagnostics and observations. We don't forward model emission spectra in these simulations. We literally just count the number of oxygen atoms versus the number of hydrogen, right? Is that a fair comparison? There's a lot of different difficult questions they have to answer there.
Yep.
You said it while you're picking and symbol that it was hard to understand the implications of the assumptions and things. Like you try, but it's very difficult.
Yeah.
I'd like to hear more.
I have a couple papers for you. Yeah. So it is really difficult. So for example, right, I can sort of do this exercise in illustrious TNG, maybe with this plot here, right? So illustrious TNG is the thing in the middle here. And in the illustrious TNG model, the mass loading factors, right, the things I complained about in Simba, also have some sort of strange dependence on them. Specifically, they also have a redshift dependence and some mass dependence. And so as you go further and back in time in illustrious TNG, things tend to have more similar mass loading factors, and then they diverge as you get to lower redshift. Right, and so you can sort of see maybe like at redshift 8, 7, 6, whatever, the slope of this line is more similar than it is than at redshift 0, for instance. And so there are things that you can do, right? It's not that this is impossible, but it is more difficult. For example, like illustrious versus TNG, right? This is illustrious TNG. TNG stands for the next generation, right? The next generation of illustrious simulations. These things are like nominally cousins, and they disagree pretty strongly. They run with the same hydrodynamics code, a lot of the same physics, though there are detailed implementation differences. And even at that sort of simplifying limiting case, it's difficult to pinpoint exactly what's going on.
So when I looked at your mass metallicity relation compared to observations, as I remember, I think TNG had the best agreement.
Yeah, that's right.
Curious whether it was a consequence of calibration or what it's a solution for the TNG.
Yeah, so I think for the reason I stated for Yanbo's question is I wouldn't calibrate on the normalization of the mass metallicity relationship, right? The normalization of the MZR in observations is a mess, right? Just by itself, you can use different emission diagnostics and get a totally different normalization on the same exact systems. And so certainly the TNG model was not directly calibrated on finding this normalization, right? Paul did a great job implementing this though. And we do happen to get this diagnostics mass metallicity relationship pretty close. But I would say it's somewhere between, not to discredit the work Paul did, right? It's somewhere between a coincidence and something I wouldn't read too far into. Like I said, not to discredit Paul too much.
Shut that down.
Thanks, Alex, for the great talk. So my question is more about like concepts of how you can make progress in the field in the future. So you hinted at this with the comment that, for example, the energy that a supernova ejects into the medium, the specific values that you can use. So all these sockets that you need to put into your simulations like stellar evolution and say supernova covariance, stuff like that. Do you need to wait for those fields to like figure their stuff out? Or do you think those specific values won't matter that much because they smoothen out on this like last statistical samples? So what do you think about that? Like, is it more constant by things that you have to do in your simulations, or is it constant by the uncertainty in their like things?
Yeah, great question. So certainly uncertainty on precision numbers like the energy per supernova, right, which may not even itself be a precision number, can have distinct impacts. But I actually think one of the advantages of this approach that we're taking is being agnostic to that number. And we can, in this way, sort of make like a feedback loop, right? Pun maybe intended. And have some observational signature from populations of galaxies, from supernova values that are 6 times 10 to the 51 ergs, right? And this will presumably make some galaxy populations that are not so realistic, right? And so you can, in that way, sort of maybe, go back to, I'll tell Rafi, by the way, it's not 6 times 10 to the 51, right? It's only whatever. It has to be in this range, right? And there's a nice feedback loop. There's a nice communication, a nice dialogue that can go on there.
I think we're going to take one last question up there, please.
So first feedback is it observed across redshift and fire simulations, or does it stop?
Yeah, the emergence of disks happens around redshift 1, which is basically what I would think of as like when your system stops being super bursty. Like you go from these weird gas clumps to having a disk galaxy that looks like a Milky Way at redshift 0. That transition happens around redshift 1 in the simulation. So your potential well gets deep enough, and so when your supernovae all go off, it's not necessarily going to totally destroy the system.
So with that, I would like to thank all of you guys for coming and for your engagement and your many great questions. Thank you for that. Thanks to the folks online who joined us for this talk. We are now going to kick you all out while we adjourn into a private session with the Thesis Defense Committee. And let's thank Alex one more time.